Have you ever just wished you could see what's coming next? You know, what the weather will be like tomorrow, which way the market's going to turn, or even how people will behave? It's this universal desire we all have, right? To predict the future. Well, today, we're going to unpack a super powerful mathematical tool that helps us do just that. And the secret? It's all about focusing only on the present. Welcome to our explainer on Markov Chains.
So here's our game plan. First, we're going to lay out the core problem we're trying to solve. Then, we'll get our hands dirty and build a toolkit with all the key concepts you need to know. After that, we get to the really fun part. We'll put these tools to the test with 3 different case studies so you can see them in action. And finally, we'll look ahead and explore how you can take this incredible method and apply it to your own research. Okay, let's jump right in. This first section is all about setting the stage. See, before we can get to the how, we really need to understand the why. At its heart, so much of research is really just about trying to model and understand change. And that's exactly the puzzle we're tackling today.
And this right here, this is the central question for our entire discussion. The real beauty of the method we're about to explore lies in this one powerful idea. It's called the Markov property, and it's the assumption that you don't actually need to know the entire history of a system to figure out its next move. All that matters is where it is right now. Okay, so to answer that big question, we're going to need the right tools. In this section, we're going to define the 3 key concepts that act as the engine for any Markov chain model. Let's go ahead and build that foundation. First up is the Markov chain itself. The best way to think about it is as a memoryless process. The system literally doesn't care how it got to where it is today. It could have been a long, complicated journey or a straight shot. Its next move, its future, depends only on its present. And that right there is the crucial point. Next, we have the engine of our model, the stochastic matrix. You can think of this thing as the rule book. Each and every number inside this matrix tells you the exact probability of moving from one state to another. And because they're probabilities, every number is going to be between 0 and 1. And, this is key, each row has to add up to exactly 1 because that accounts for all the possible outcomes. Now this table really makes that abstract idea concrete. We're looking at a stochastic matrix for radio listeners. So, if you're listening to the news right now, there's a 70% chance you'll still be listening after the commercial break, and a 30% chance you'll flip over to music. But check this out. The music listeners are a bit less loyal. There's a whopping 60% probability they'll switch over to the news. This simple little table captures the entire system's behavior perfectly. And our final tool is the state vector. This is basically just a snapshot of the system at one specific moment in time. So if the matrix is the rulebook, the state vector is the current score of the game. For our radio example, a vector like 0.8, 0.2 would tell us that right now 80% of the audience is listening to the news and the other 20% is listening to music. Simple as that. All right, we have our tools. The memoryless chain, the transition matrix as our rulebook, and the state vector as our snapshot. Now it's time to put them to work. Let's get into our case studies and see how this all comes together to make some seriously powerful predictions. Okay, let's head back to that radio station. The setup is straightforward. At 8:15 in the morning, absolutely everyone is tuned into the news station. So the question is, after 2 station breaks, where is that audience going to be? Here's how we figure it out. We start with our initial state vector, which is 0, 1, because 100% of listeners are tuned to the news. To see what happens after the first break, we just multiply this vector by our stochastic matrix. Then to find out what happens at 9:25 a.m., we just do it again. We take that new state vector and multiply it by the same matrix. And there's our result. After just 2 transitions, the audience has shifted in a big way. That initial 100% news audience is now split, with about 67% still listening to news, but a full 33% listening to music. Now, this isn't just a number. For the radio station, losing a third of your core audience in about an hour, well, that could have a real impact on something like advertising revenue. Okay, let's try a problem that's a little more complex. This time, we've got a lab animal with 3 different food choices. And this animal seems to be a creature of habit. There's a 50% chance it'll stick with the same food it ate yesterday. But if it does decide to switch, it splits its choice evenly between the other 2 options. So here's the 3x3 stochastic matrix that models this behavior. You can see those 0.50 probabilities running right down the diagonal. That's the chance of staying with the same food. Everything else is 0.25. So here's the question. If the animal starts on day 1 eating food #1, what's the probability that it chooses food #2 2 days later? And the answer is 31.25%. We get this by doing the exact same process as before. We start with a vector of 1, 0, 0, and we multiply it by our matrix twice. The model takes what might feel like a fuzzy guess and turns it into a precise, quantifiable prediction. Pretty cool, huh?
For our last case study, let's look at something with some real-world public health implications. We've got a student population that can be in one of two states, healthy or ill. The transition probabilities are pretty clear. Being healthy is a very stable state, while being ill is, well, less so. We're going to start on a Monday, with 20% of the student body being ill.
Now just look at the story this bar chart tells. Using our model, we can actually forecast the trend. That initial 20% of ill students on Monday is predicted to drop to 12% on Tuesday, and then down to just 8.4% by Wednesday. This shows a really clear trend towards recovery, and that's vital information if you're trying to predict when, say, campus health services might see a drop in demand.
So these examples show how the model works. But, this isn't just about solving textbook problems. This is an incredibly flexible and powerful tool. The real question is, how can you, as a researcher, take this and apply it to your own work?
The possibilities here are absolutely vast. If you're in the social sciences, you could model how public opinion shifts on a major issue. In economics, you could predict customer brand loyalty. Biologists can use this to track genetic mutations through generations. Public health officials can forecast the progression of chronic conditions in a population, and climatologists can even model daily weather patterns. All right, let's bring this all home. We've defined the tools, we've walked through the applications, we've explored the incredible potential. So what is the big takeaway here? It's this. Markov chains give us a framework that is both incredibly powerful in its ability to predict and, at the same time, surprisingly accessible in its logic. By just focusing on a system's states and the probabilities of moving between them, you can start to model the evolution of some really complex systems. And that really is the heart of it. We might never know the future with 100% certainty, but that doesn't mean it's a complete mystery. With the right tools, like the one we've talked about today, we can model the probabilities and make much, much more informed predictions about what's to come. So I want to leave you with this final thought. A challenge, really. Take a look at your own research, at your own field of interest. What process, what system, what kind of behavior could you break down into a set of states and the transitions between them? Seriously, think about it, because the answer to that question might just be the start of your next great research project.